So let me get this straight. There's a black hole the mass of 33 suns just floating around less than 2,000 light years from Earth, and we only found it last year?
April 2024, to be exact. And before you ask, yes, astronomers are slightly embarrassed about this.
Slightly? Elena, this thing is a cosmic monster. How do you lose track of something that massive?
Well, it helps when the monster is literally invisible and makes no sound.
Touché. But seriously, 33 solar masses? That's not just big. According to everything I've read, that's not supposed to exist in our galaxy at all.
And that's exactly why Gaia BH3 is causing existential crises in astrophysics departments worldwide. Welcome to the 33 solar mass monster hiding 1,926 light-years away. I'm Dr. Elena Vasquez.
And I'm Marcus Chen, here to ask the questions that'll probably make Elena regret agreeing to this podcast. Today, we're talking about the most massive stellar black hole ever discovered in the Milky Way. And trust me, this story has everything. Invisible monsters, ancient stars, detective work involving wobbles, and scientists who literally said, this shouldn't exist.
It's like reality looked at our textbooks and said, that's cute.
So buckle up, because we're diving into a discovery that's rewriting the rules about what's lurking in our cosmic neighborhood.
All right, Elena, let's start with the basics. April 16th, 2024. What happened?
The European Space Agency dropped a bombshell. The Gaia Spacecraft, which has been mapping stars since 2013, detected a black hole that weighs 32.7 solar masses, give or take less than one solar mass. They named it Gaia BH3.
32.7 solar masses. Let me do the math here. That's roughly 11 million times Earth's mass?
Correct. And it's compressed into a region about 195 kilometers in diameter. For perspective, that's roughly the distance from, say, Washington, D.C. to Philadelphia. 33 suns squeezed into something smaller than many asteroids.
Okay, that's genuinely terrifying, but here's what I don't get. The Gaia spacecraft has been operational since 2013. Why did it take over a decade to find this thing?
Because finding dormant black holes is like trying to spot an invisible ninja in a dark room who's also taking a nap. Gaia doesn't actually see the black hole, it sees the effect of the black hole.
The wobble method?
Exactly. Gaia is an astrometry mission, meaning it measures the precise positions and movements of stars with ridiculous accuracy. We're talking 24 micro-arcseconds. That's like measuring the width of a human hair from 1,000 kilometers away.
That's absurd precision.
It has to be, because what Gaia detected was a star doing a little dance, a subtle back and forth motion as it orbits around something invisible. When you have a binary system, both objects orbit their common center of mass. If one object is invisible but massive, the visible star traces an ellipse through space.
So they're both dancing around each other, but we can only see one dancer.
Perfect analogy. And by measuring how that visible star moves, the size of its orbit, its period, its velocity, you can calculate the mass of the invisible partner using Kepler's laws.
Okay, but Gaia has been observing billions of stars. How do you spot one specific wobble among all that data?
That's where it gets interesting. The lead researcher, Pasquale Panuzzo from CNRS in France, was analyzing preliminary data for Gaia's data release 4. He noticed this particular star in the constellation Aquila exhibiting an anomalous orbital motion. The wobble was too large, too pronounced. Something massive was pulling on it.
And he thought that's not normal.
He thought that's either a measurement error or the discovery of a lifetime. So they did follow-up observations using ground-based telescopes, the Very Large Telescope in Chile, the Mercator Telescope in Spain, observatories in France. They needed to confirm this wasn't just a glitch in the data.
And it wasn't.
It very much wasn't. The spectroscopic data confirmed everything. They were looking at a star orbiting an invisible companion with a mass of 33 suns. The only thing that massive and invisible is a black hole.
No other options?
None that fit. Too massive to be a neutron star, those max out around 3 solar masses. Too compact to be a cluster of smaller objects. It had to be a black hole, which meant they just found the most massive stellar origin black hole in the Milky Way.
And Panuzzo's exact quote was, "This is the kind of discovery you make once in your research life."
Can you blame him? Most astronomers go their entire careers without finding something that fundamentally challenges existing models. He found a black hole that, according to our best theories, shouldn't exist in our galaxy.
Wait, hold up. Shouldn't exist? That's a hell of a statement. Why shouldn't it exist?
Because of something called the stellar mass gap, or what we thought was a gap. Before Gaia BH3, stellar evolution models predicted that black holes formed in the Milky Way couldn't exceed about 20 solar masses.
And this thing is 33.
Which is 65% heavier than the previous record holder, Cygnus X1. That's not a small discrepancy. That's a rethink your models level discrepancy.
All right, I'm hooked. But before we get into why this breaks the models, I need to know, where is this thing? You said constellation Aquila.
Yes. The exact coordinates are right ascension, 19 hours, 39 minutes, 18.7 seconds, declination, plus 14 degrees, 55 minutes, 54 seconds, if you want to point your telescope at it. But that won't help you see it.
Because it's invisible?
Because it's 1,926 light years away and emitting absolutely no light. The companion star, you can see, barely, but the black hole itself is just a region where starlight goes to die.
1,926 light years. That's relatively close in cosmic terms, right?
Uncomfortably close, actually. When they announced this discovery, it became the second closest known black hole to Earth. Only Gaia BH3 at 1,560 light years is closer.
Should I be worried?
Not even slightly. At that distance, Gaia BH3 has less gravitational influence on you than the coffee cup on your desk. But we'll get to the "is this dangerous" question later, because I know you're dying to ask it.
You know me too well. Okay, so let's talk about why this thing shouldn't exist. You mentioned stellar evolution models predicted a 20 solar mass limit. Walk me through the logic.
Sure. So when a massive star, let's say 25 to 30 solar masses at birth, goes through its life cycle, it loses mass, a lot of mass. These stars have incredibly powerful stellar winds that blow material off their surface throughout their lifetime.
Like the solar wind from our sun?
Same principle, vastly more intense. Our sun loses about 1 billion kilograms per second through solar wind. That sounds like a lot, but it's a tiny fraction of the sun's total mass. Massive stars lose material at much higher rates.
Because they're burning hotter and faster.
Exactly. The more massive a star, the shorter and more violent its life. And then comes the finale, the supernova explosion. When the core collapses, there's this incredibly energetic explosion that blows off huge amounts of material. By the time you're left with a black hole, conventional wisdom said you'd have maybe 10 to 20 solar masses at most, not 33.
But LIGO has been detecting black holes merging at around 30 solar masses for years now, so we knew they existed.
Right, but those are always in distant galaxies, hundreds of millions of light years away. We could wave our hands and say, well, maybe conditions were different there, maybe metallicity played a role. But Gaia BH3 is here, in our galaxy. That means we can't ignore it.
Metallicity. You're gonna have to explain that one for the audience.
Absolutely. In astronomy, metals means anything heavier than hydrogen and helium. So carbon, oxygen, iron, all metals to us.
Which is deeply weird to anyone who remembers high school chemistry.
Astronomers are special like that. But here's why it matters. Metals in a star's atmosphere help drive stellar winds. More metals means stronger winds, which means more mass loss during the star's lifetime. The sun has about 2% metals by mass. We call that solar metallicity.
And Gaia BH3's companion star
has a metallicity of negative 2.56 on the logarithmic scale, which means it has about 100 times fewer metals than the sun. It's what we call a metal-poor star.
And fewer metals means
weaker stellar winds, less mass loss, which means the progenitor star, the star that collapsed to form the black hole, retained much more of its original mass.
When it went supernova and formed the black hole, there was simply more material available to become the black hole.
So the secret to making a supermassive stellar black hole is starting with a metal-poor star.
That's exactly the theory, and Gaia BH3 is the smoking gun evidence. This has been hypothesized for years, but we've never had proof in our own galaxy until now.
Okay, but here's what I don't get. If low metallicity is the answer, and low metallicity was common in the early universe,
then there should be more of these massive black holes around, yes. And that's the million-dollar question. Either we've been incredibly unlucky in our detections, or most of these ancient massive black holes formed in environments that were different from Gaia BH3.
You're about to tell me something about where this thing came from, aren't you?
Oh, the origin story is wild. So the companion star, the one doing the wobble dance, isn't just metal poor, it's ancient. We're talking 12 to 13 billion years old.
The universe is 13.8 billion years old.
Right. This star formed when the universe was barely a billion years old. It's a genuine relic from the cosmic dawn. And here's the kicker. Both the black hole and the companion are associated with something called the ED2 stellar stream.
Which is?
It's the remnants of an ancient globular cluster that the Milky Way cannibalized more than 8 billion years ago. Globular clusters are these dense balls of stars, think hundreds of thousands of stars, packed into a relatively small region. Our galaxy has eaten dozens of smaller galaxies and clusters over its lifetime.
So these two objects were part of a cluster that doesn't exist anymore.
Exactly. The Milky Way's gravity tore the cluster apart, and the debris formed the stream of stars moving through our galaxy. Gaia BH3 and its companion are part of that stream, which tells us they have a shared origin.
But here's what's weird to me. If they formed in a globular cluster, those places are chaotic. Stars are constantly passing by each other, gravitational interactions are happening all the time. Is it possible the black hole and the star weren't originally together?
That's one of the leading theories, actually. Some simulations suggest the black hole and the companion star could have been introduced through dynamic interactions within the cluster. Maybe the black hole stole the star from another system, or maybe they were both wandering and got captured into a binary.
cosmic matchmaking via gravitational chaos?
I love that, but yes, essentially. And there's evidence for this in the companion star's chemical composition.
You're about to blow my mind, aren't you?
Maybe a little. So when a massive star goes supernova, it forges heavy elements and blasts them into space. If a companion star is nearby during that explosion, it gets contaminated with all these freshly made elements. Carbon, oxygen, iron, you name it.
Like getting hit by nuclear shrapnel.
Exactly. And we see this all the time in binary systems with X-ray binaries. But here's the thing, Gaia BH3's companion star is pristine. It shows no evidence of contamination from a supernova.
Wait, what?
Elisabetta Kafau, one of the researchers who analyzed the stellar spectrum, literally said there is no evidence that this star was contaminated by the material flung out by the supernova explosion. The star's composition matches other ancient metal poor stars perfectly.
So either the black hole formed without a traditional supernova,
or the two objects weren't together when the black hole formed. They could have been brought together later through gravitational interactions in the cluster.
That's actually kind of beautiful. They found each other after the black hole's violent birth and have been dancing together for billions of years.
Marcus, are you going soft on me?
I contain multitudes. But okay, let's talk about the dance itself. What's this orbital system actually look like?
So they orbit their common center of mass once every 11.6 years. The orbit is highly eccentric, eccentricity of about 0.73, which means it's pretty stretched out, not circular. At closest approach, they're about 4.5 astronomical units apart. That's roughly the distance from the Sun to Jupiter. At their farthest, they're about 29 AU apart, similar to Neptune's orbit.
So they're doing this huge elliptical dance over more than a decade.
And the mass ratio is absurd. 43-1 in favor of the black hole. The black hole weighs 32.7 solar masses. The companion star weighs about 0.76 solar masses, which is less than our sun.
So the star is just getting dragged around by this gravitational giant.
Pretty much. But here's what's important. The separation is far too large for any mass transfer to occur. The star is well within its Roche lobe, meaning it's not being tidally stripped or torn apart. There's no accretion disk, no material flowing onto the black hole, nothing.
Which is why it's dormant.
Exactly. A dormant or sleeping black hole. No food means no accretion, which means no X-rays, no visible light, no radio emissions. It's gravitationally there, but electromagnetically silent.
Invisible and quiet. The perfect predator.
Except it's not actually predatory. That's a common misconception we should address.
Oh, I'm sure our listeners would love to hear this. Actually, black holes aren't cosmic vacuum cleaners.
Mock me all you want, but it's true. Black holes only consume things that get too close. If you replace the sun with a black hole of equal mass, which is impossible, but hypothetically, Earth would continue orbiting exactly as it does now. We'd freeze, because no sunlight, but our orbit wouldn't change.
Because gravity depends on mass, not on whether that mass is a black hole or a star.
Right, and at 1,926 light-years away, Gaia BH3 has zero effect on Earth. The gravitational force drops off with the inverse square of distance. By the time you're talking about thousands of light-years, the influence is negligible.
All right. I'll let our listeners sleep soundly tonight. But before we move on, I want to ask, what happens to this system in the future? The companion star is a G-type giant, so it's evolving, right?
It is. It's already evolved past the sun's current stage. It's about 5 times larger than the sun, with 15 times the luminosity. It'll continue expanding through its red giant phase, eventually shed its outer layers and leave behind a white dwarf.
And the black hole?
We'll continue orbiting with the white dwarf remnant for billions of years. The black hole won't consume it. They'll just keep dancing.
Eternal partners in a gravitational waltz. Okay, that's definitely beautiful.
See, I'm converting you to the romance of astrophysics.
Don't push your luck. Let's take a quick break, and when we come back, we're going to talk about how Gaia actually finds these invisible monsters. Welcome back. We're talking about Gaia BH3, the most massive stellar black hole ever found in the Milky Way. And before the break, Elena promised to explain how the Gaia spacecraft is revolutionizing black hole astronomy. So, Elena, sell me on Gaia.
All right. The Gaia spacecraft, launched by the European Space Agency in December 2013, is basically the most ambitious stellar census ever attempted. It spent over 11 years making more than 3 trillion observations of 2 billion astronomical objects.
3 trillion observations. That's an absurd number.
It's what you need when your goal is to create the most precise 3-dimensional map of our galaxy ever made. Gaia measures positions, distances, and motions of stars with accuracy down to 24 micro-arcseconds. To put that in perspective, if you were in New York and someone in Los Angeles moved a dime 1 millimeter, Gaia's precision is equivalent to detecting that motion.
That's not possible.
And yet here we are. Gaia sits at the L2 Lagrangian point, about 1.5 million kilometers from Earth, continuously scanning the sky. It has 2 telescopes that feed into a 1 billion pixel camera, the largest ever flown in space.
And it's been doing this for over a decade?
Yes, though the mission officially ended in November 2024, but the data processing continues. Gaia Data Release 3 came out in 2022, and Data Release 4 is expected in late 2025 or 2026.
And that's where Gaia BH3 came from? Preliminary analysis for DR4.
Exactly. The discovery was so significant, they did an early announcement in April 2024 before the full data release. They literally couldn't wait to share it.
Okay, so Gaia is incredibly precise, but how does precision translate into finding black holes?
Because black holes reveal themselves through their gravitational effects on companion stars.
When a star orbits a black hole, it's constantly accelerating, speeding up and slowing down, moving toward us and away from us. Gaia measures these tiny shifts in position over time.
The wobble we talked about earlier.
Right. But the wobble for Gaia BH3's companion star is incredibly subtle. We're talking about angular movements measured in milli-arcseconds across an orbital period of 11.6 years. You need Gaia's precision to detect that.
And before Gaia, we just couldn't find these systems?
We could find active systems, X-ray binaries, where material is flowing onto the black hole and producing radiation. But dormant black holes in wide binaries, basically impossible to detect. Gaia opened up an entirely new class of black hole discovery.
How many black holes has Gaia found so far?
3 confirmed. Gaia BH1 in November 2022, Gaia BH2 in 2023, and Gaia BH3 in April 2024. But here's the exciting part. Data Release 4 is expected to reveal about 30 more black hole systems, and DR5 could find 45 additional ones.
So we're going from knowing about 20 stellar mass black holes in the Milky Way to potentially knowing about 100 in the next few years.
At least, and that's going to completely revolutionize our understanding of black hole populations.
Let's talk about those populations. How many black holes are actually out there?
Current estimates suggest the Milky Way contains between 100 million and 1 billion stellar mass black holes.
Pause. I'm sorry, what?
100 million to 1 billion.
Elena, we've confirmed about 25. That's a detection rate of 0.000025%. That's embarrassing.
Welcome to astronomy. The vast majority of black holes are isolated. No companions, no accretion, nothing to give them away. They're just gravitationally dense objects drifting through the galaxy, completely invisible.
So there could be black holes relatively close to us and we'd have no idea.
NASA estimates the nearest isolated black hole could be as close as 80 light-years from Earth. There's even speculation about black holes in the Hyades cluster at 150 light-years, though none have been confirmed.
80 light-years. I don't know if I should be excited or terrified.
Excited, definitely excited. Because even at that distance, the gravitational effects are negligible, but it means we're living in a galaxy full of invisible gravitational giants we're only now learning to detect.
Okay, but let's compare Gaia's method to other detection techniques. We've got X-ray astronomy, gravitational waves. How does Gaia fit in?
Each method finds different populations. X-ray astronomy finds active systems where material is accreting onto the black hole, heating up and emitting X-rays. These are relatively rare. You need a close binary with active mass transfer.
And gravitational waves?
Gravitational wave detectors like LIGO and Virgo capture the final moments before black hole mergers, 2 black holes spiraling into each other and colliding. But these are always in distant galaxies, hundreds of millions to billions of light years away. You can't use gravitational waves to detect stable binary systems in the Milky Way.
So Gaia finds the quiet ones, the dormant systems that aren't feeding and aren't colliding.
Exactly. And it turns out that dormant black holes in wide binaries might be more common than X-ray binaries. We just couldn't see them before.
George Seabrook from University College London had a great quote about this, comparing Gaia's discoveries to Neo seeing the Matrix for the first time.
Love that. Yes. Finding Gaia BH3 is like the moment in the Matrix where Neo starts to see the Matrix. In our case, the Matrix is our galaxy's population of dormant stellar black holes, which were hidden from us before Gaia detected them.
I love that quote because it captures the paradigm shift. We thought we knew what was out there, and suddenly Gaia reveals this entirely hidden population.
And it's not just black holes. Gaia is transforming our understanding of stellar streams, galactic structure, stellar evolution, everything. It's detected 500,000 variable stars, found hundreds of thousands of asteroids, discovered new stellar populations. The black holes are just one highlight.
But let's be honest, black holes are the sexiest highlight.
I mean, yes, you can't compete with invisible monsters. But the point is that Gaia has become the discovery machine of the decade, and it's not done yet.
You mentioned data releases 4 and 5. What's coming?
Data release 4 will include better astrometry for fainter objects, improved radial velocities, more detailed stellar parameters. We'll probably see dozens of new black hole candidates that need follow-up confirmation. DR5 will push even further, potentially finding 45 additional black hole systems.
And after Gaia?
The Nancy Grace Roman Space Telescope, launching in late 2026 or 2027, will use gravitational microlensing to detect wandering black holes, isolated objects that pass in front of background stars and magnify their light. That could find hundreds of black holes, including potentially primordial black holes from the Big Bang.
So we're entering a golden age of black hole discovery.
Absolutely. And it all started with Gaia looking at stellar wobbles.
Okay, I want to go back to something you mentioned earlier, Gaia BH1 and Gaia BH2. How do they compare to BH3?
Great question. Gaia BH1 was announced in November 2022, and it was the first unambiguous detection of a dormant black hole using astrometry. It's about 10 solar masses, located 1,560 light-years away, and has an orbital period of 186 days.
So much closer orbit than BH3.
Right. Then came Gaia BH2 in 2023, about 9 solar masses, 3,800 light-years away, orbital period of 3.5 years. Both of these are normal stellar mass black holes. Then BH3 shows up at 33 solar masses, and everyone's minds explode.
Because it's 3 times more massive than the others.
And because it proves that the LIGO mass distribution, the 30 solar mass peak we see in gravitational wave detections, exists locally. Before BH3, we could speculate that massive black holes only formed in distant galaxies with different conditions. Now we know they're here.
And that changes everything.
It validates theories about metal-poor star evolution. It suggests there's a population of massive dormant black holes we haven't found yet. And it raises questions about formation mechanisms. Are these coming from isolated stellar collapse or dynamic formation in clusters?
So you're telling me we still don't know how Gaia BH3 formed?
We have theories, but no definitive answer. The fact that it's associated with the ED2 stream suggests cluster origins, but whether it formed in isolation or through stellar interactions is still debated.
So even with this incredible discovery, we're left with more questions than answers.
Welcome to astrophysics. Every answer generates 10 new questions.
Fair enough. All right, we need to talk about what it would actually be like to approach Gaia BH3, because I know the audience is dying to visualize this thing.
Okay, it's time to tackle the impossible question, what does Gaia BH3 actually look like?
That's delightfully tricky, because by definition, the black hole itself is invisible. No light escapes from within the event horizon.
Right, but there's gotta be something we can visualize. Give me the event horizon size.
For a black hole of 33 solar masses, the event horizon, the point of no return, extends to about 195 kilometers in diameter. That's roughly the distance between 2 mid-sized cities.
So you're telling me that 33 suns worth of material is compressed into something the size of, what, the distance from Boston to Providence?
More or less. And despite packing all that mass into that volume, the actual black hole is smaller than many asteroids we've visited with spacecraft.
That's genuinely mind-bending. What about the immediate surroundings?
That's where things get interesting, because Gaia BH3 is dormant. No accretion disk, no infalling material, there's no glowing structure, but there is warped spacetime.
Explain that for someone who doesn't have a PhD in general relativity.
Okay, so Einstein showed us that mass warps the fabric of spacetime. The more concentrated the mass, the more severe the warping. Near a black hole, spacetime is so curved that it bends the path of light.
So if you were looking at Gaia BH3 from a distance,
you'd see a region where background starlight gets distorted. Stars would appear stretched, bent around an invisible point. If a star happened to pass directly behind the black hole from your perspective, its light would form an Einstein ring, a complete circle of light wrapped around the dark shadow.
Like looking through a gravitational lens.
Exactly. And the closer you get, the more extreme the distortion. There's something called the photon sphere at 1.5 times the event horizon radius, about 292 kilometers from the center. At that distance, light can actually orbit the black hole.
Wait, light can orbit?
Temporarily. Photons traveling tangent to the photon sphere can complete orbits before escaping or falling in. It creates these nested rings of increasingly red-shifted light.
Redshifted because the light is climbing out of a gravitational well.
Right. The deeper in the well, the more energy the light loses, which stretches its wavelength toward the red end of the spectrum. If you were hovering just above the event horizon, you'd see the universe blue shifted above you and red shifted in every other direction.
That's trippy. What about time dilation? I've heard that time slows down near black holes.
It does, from the perspective of a distant observer. If you were falling toward Gaia BH3, your watch would tick normally from your perspective. But to someone watching from far away, your watch would appear to tick slower and slower as you approach the event horizon.
And once you cross the event horizon?
From the distant observer's perspective, you'd appear to freeze at the event horizon, red-shifted into oblivion. From your perspective, you'd cross normally, but then things get unpleasant fast.
Spaghettification.
Yes, the technical term. The tidal forces near the singularity are extreme. Your feet would experience stronger gravity than your head, stretching you into impossibly thin strands.
And this happens because?
Because the gravitational field gradient is steep. The difference in gravitational acceleration between your feet and head becomes enormous. At some point, even atoms get torn apart.
Delightful. So crossing the event horizon is a one-way ticket to becoming cosmic spaghetti.
Yes, for stellar mass black holes. Interestingly, for supermassive black holes, millions or billions of solar masses, the tidal forces at the event horizon are much weaker. You could potentially cross without immediate spaghettification.
But you're still doomed.
Oh, absolutely. Once past the event horizon, all paths lead to the singularity. It's less a place than a moment in your future, an inevitable destination.
Okay, that's sufficiently terrifying. Let's talk about scale comparisons, because I think people struggle to grasp just how dense black holes are.
Sure. Gaia BH3 is about 11 million times Earth's mass and 17,000 times Jupiter's mass, all compressed into that 195-kilometer sphere. If you could somehow compress Earth to black hole density, it would fit into a marble.
A marble containing the entire planet.
Right. And the density near the singularity is theoretically infinite. All the mass concentrated in a point of zero volume.
Which is probably where our physics breaks down.
Definitely where our physics breaks down. General relativity predicts infinite density, but we know that can't be physically accurate. We need a theory of quantum gravity to understand what actually happens at the singularity.
So the singularity is less a real thing and more here be dragons on the map of physics.
I love that. Yes, it's where our equations fail and we admit we don't know what's going on.
All right, so we've established that Gaia BH3 is invisible, dense beyond comprehension, and surrounded by warped space-time. But you mentioned earlier that it poses no threat to Earth. Walk me through why.
Because gravity obeys the inverse square law. The gravitational force between two objects drops off with the square of the distance. At 1,926 light years, that's about 18 quadrillion kilometers. The gravitational pull from Gaia BH3 on Earth is negligible.
Less than my coffee cup?
Less than a dust mote in Australia would pull on you if you're in North America. The moon, at 384,000 kilometers, exerts incomparably more gravitational force on Earth than Gaia BH3 ever could.
What about the radiation? Don't black holes emit Hawking radiation?
They do, theoretically, but it's inversely proportional to mass. For a black hole as massive as Gaia BH3, the Hawking radiation temperature is about 2 nanokelvins. That's 0.0000002 degrees above absolute zero. It's emitting less energy than it receives from the cosmic microwave background.
So it's actually absorbing more energy than it's emitting?
Exactly. In practice, Hawking radiation is only significant for tiny primordial black holes. For stellar mass and supermassive black holes, it's negligible.
Okay, but here's the question everyone wants to know. What if Gaia BH3 were closer? What if it was, say, 1 light year away?
At 1 light year, still no immediate danger. You'd need it within the Oort cloud, roughly half a light year, before gravitational perturbations might affect comets. But let's be clear, Gaia BH3 is following a retrograde orbit through the galaxy. It's traveling in the different direction than our solar system, and there's zero chance of collision.
Retrograde orbit means...
It's orbiting the galactic center in the opposite direction from most stars in our neighborhood. Plus, it has a large inclination to the galactic disk plane. It's bobbing up and down through the disk rather than staying level with it.
So it's basically on a completely different trajectory.
Completely different. It's part of the ED2 stream, remember? The remnants of a cannibalized globular cluster. Those objects have chaotic orbits compared to the orderly rotation of disk stars like our sun.
So I can sleep soundly knowing that Gaia BH3 won't eat Earth.
You can sleep soundly knowing that even if Gaia BH3 somehow teleported to Alpha Centauri's distance, 4.4 light years, you still wouldn't notice any gravitational effects in your daily life.
Good to know. Okay, one more visualization question. If we sent a probe to Gaia BH3, what would it see on approach?
That's a great thought experiment. So, as your probe approaches, the first thing you would notice is the companion star, the G-type giant that's doing the wobble dance. It's about 5 times larger than our sun, putting out 15 times the luminosity with a distinct orange-yellow color.
And it's ancient.
12 to 13 billion years old, one of the oldest stars in the galaxy. The probe would measure its spectrum and see that extreme metal deficiency, 100 times less than the sun.
And as you get closer to the black hole itself,
you'd start seeing the gravitational lensing effects. Background stars would appear distorted, bent around an increasingly obvious dark region. The probe's instruments would measure the gravitational gradient, the pull getting stronger as you approach.
no accretion disk?
None. Remember, this is a dormant system. The companion star is too far away, 4.5 AU at closest approach, to transfer material. So there's no glowing disk, no jets, no radiation, just the stark contrast between the black hole's gravitational presence and its electromagnetic absence.
The ultimate cosmic void.
In a sense, yes. Though void is misleading, it's incredibly dense. But electromagnetically, it's as close to nothing as you can get.
All right, I think we've painted a sufficiently vivid picture of this invisible monster. Now we need to talk about the bigger implications. What does Gaia BH3 tell us about the universe?
Welcome to the final segment. We've spent the minutes talking about Gaia BH3 specifically, but now I want to zoom out. Elena, what does this discovery tell us about the universe more broadly?
It tells us that our models were incomplete. Not wrong necessarily, but incomplete. We built theories about stellar evolution and black hole formation based on what we could observe. X-ray binaries, gravitational wave sources, but we were missing an entire population.
The dormant massive black holes.
Right, and Gaia BH3 proves they exist. It validates theories about metal-poor stellar evolution producing massive black holes. It shows that the LIGO mass distribution isn't unique to distant galaxies. It exists in our cosmic neighborhood.
So the 30 solar mass black holes LIGO detects aren't anomalies.
They're part of a spectrum, and that has huge implications for how we think about gravitational wave sources. Where do those merging black holes come from? How do they form? Gaia BH3 gives us a local laboratory to study the formation mechanisms.
You mentioned earlier that there's debate about whether it formed through isolated stellar collapse or dynamically in a cluster.
Yeah, and that's crucial. If massive black holes form primarily through stellar collapse, that tells us one thing about metallicity and stellar winds. If they form through dynamic interactions in dense clusters, mergers, captures, exchanges, that tells us something different about the environments that produce them.
And we don't know which it is?
Not definitively. The ED2 association suggests cluster origins, but simulations are still being refined. A paper from October 2025 favored dynamical formation, but others argue for direct collapse. More data will help settle it.
What about the companion star's pristine composition? The fact that it wasn't contaminated by the supernova?
That's one of the strongest arguments for either a direct collapse or a late-stage pairing. If they were together during the black hole formation event, we'd expect contamination. The absence suggests they either came together afterward or the black hole formed without a typical supernova explosion.
Can black holes form without supernova?
Theoretically, yes. If a star is massive enough, the core collapse can be so catastrophic that material falls back almost immediately, forming the black hole without a bright explosion. It's called a failed supernova, or direct collapse.
So the star just implodes without the fireworks?
Essentially, you get a brief neutrino burst, but minimal electromagnetic emission. These events are incredibly hard to detect, which is why we're not sure how common they are.
And if Gaia BH3 formed that way, it explains the pristine companion.
It's one explanation. The other is the dynamical scenario. The black hole and the star were brought together millions or billions of years after formation. Both are plausible.
Okay, bigger picture question. How many more Gaia BH3s are out there?
That's the billion-dollar question, literally. We know from LEGO that the 30 solar mass peak exists in merging black hole populations. We know from Gaia BH3 that such objects exist in our galaxy. The question is how many?
And the answer is?
We don't know yet, but data releases 4 and 5 will help. If Gaia finds more 30-plus solar mass black holes, we'll start building statistics. If BH3 is unique, that tells us something about formation rates and conditions.
What's your gut feeling?
My gut says there are probably dozens to hundreds of massive, dormant black holes in the Milky Way, mostly in metal-poor populations. But that's speculation. We need data.
And future missions like Roman will help?
Absolutely. Roman will use gravitational microlensing, which works even for isolated black holes with no companions. That could find hundreds of wandering black holes throughout the galaxy.
Wandering black holes. That's somehow more terrifying than stationary ones.
They're not wandering with a purpose. They're just following their orbits through the galaxy. But yes, Roman could detect isolated black holes that pass in front of background stars, magnifying and distorting their light temporarily.
And that'll give us a better census of the total black hole population.
Right. Between Gaia's binary detections and Roman's microlensing, we'll finally start answering the question of how many black holes are out there and what their mass distribution looks like.
Okay, let's talk about theoretical implications for a moment. Does Gaia BH3 change any fundamental physics?
No, it fits perfectly within general relativity, but it challenges our models of stellar evolution, particularly the role of metallicity and mass loss. We need to refine those models to account for producing 33 solar mass black holes in metal-poor environments.
So it's less rewrite physics and more refine astrophysics.
Exactly. The physics is fine. Our understanding of how stars evolve and die needs updating.
What about implications for cosmology? Does this tell us anything about the early universe?
It does, actually. The companion star's age, 12 to 13 billion years, places both objects in the first billion years after the Big Bang. That's the era when the first massive stars formed and died.
The so-called population 3 stars?
Not quite. Population 3 stars were the absolute first generation, pure hydrogen and helium, no metals at all. Gaia BH3's companion has trace metals, so it's population 2, the second generation, but still incredibly ancient.
And these ancient systems tell us...
They tell us about star formation conditions in the early universe. How massive could stars get? What were the mass loss rates? How did the first black holes form and evolve? Gaia BH3 is a time capsule from the cosmic dawn.
And the fact that it survived for 13 billion years is remarkable in itself.
Absolutely. Most binary systems don't survive that long. They get disrupted by gravitational interactions with passing stars or galactic dynamics. But Gaia BH3 has remained stable for eons.
Okay, rapid fire question round for the final minutes. Ready?
Hit me.
Could there be black holes even more massive than Gaia BH3?
Possibly, yes. BH3 is the most massive we found, but there's no fundamental reason there couldn't be larger ones, especially in metal-poor populations.
What's the upper limit for stellar mass black holes?
Theoretically, maybe 60 to 70 solar masses from direct stellar collapse. Beyond that, you're probably talking about mergers or different formation mechanisms.
LIGO has detected mergers producing black holes over 100 solar masses.
Right, but those are merger products, two black holes combining. That's different from a single star collapsing to form a black hole.
Fair. Next question. How long will it take to confirm whether Gaia BH3 formed dynamically or through stellar collapse?
Years, probably. We need better simulations, more observations of the ED2 stream, and potentially detections of similar systems for comparison. Science is slow.
Could Gaia BH3's companion eventually get captured by the black hole?
No. The separation is stable, and the orbital dynamics don't suggest any decay. They'll keep orbiting for billions of years until the companion becomes a white dwarf.
And then?
Then they keep orbiting. White dwarf plus black hole dancing through the galaxy until the heat death of the universe.
Romantic. What's the coolest unanswered question about Gaia BH3?
For me, it's whether the central object is actually a single 33 solar mass black hole or a binary system, two smaller black holes orbiting each other. Current data can't distinguish between these scenarios.
Wait, it could be two black holes pretending to be one?
Potentially. Some researchers have suggested that scenario. If it's two black holes, say 15 and 18 solar masses, they'd orbit each other on a very short timescale, and we'd detect the system as a single massive object pulling on the companion star.
How would we figure out which it is?
More precise radial velocity measurements, longer observation baselines, potentially gravitational wave detection if they're close enough to merge in the next few million years. But that's speculative.
All right, final question. What does Gaia BH3 teach us about being human in a universe full of black holes?
That's very philosophical for a science podcast.
Indulge me.
Okay. I think Gaia BH3 teaches us humility. Here's this absolutely massive object, 33 times our sun, sitting relatively close to us, and we only found it last year. It reminds us how much we don't know, how much is hidden in plain sight.
The invisible giants.
Right. But it also teaches us capability. We built a spacecraft that can measure stellar wobbles across thousands of light years with absurd precision. We developed the mathematical tools to infer the existence of something we cannot see. That's incredible.
We're pretty clever monkeys.
We are. And I think there's something hopeful in that. Yes, the universe is full of invisible monsters, but we're learning to see them. We're building tools and theories that reveal the hidden structure of reality. That's worth celebrating.
Even if it keeps us up at night wondering what else is out there?
Especially then, the wonder and the terror are two sides of the same coin. Gaia BH3 is both beautiful and terrifying. An ancient relic from the dawn of time, a gravitational monster lurking in our neighborhood, and a triumph of human ingenuity that we found it at all.
That's a good place to end. Elena, thank you for walking us through this discovery. This has been incredible.
But thanks for having me, Marcus. And thanks to everyone listening for spending time with us exploring this cosmic mystery.
Until next time, keep looking up, even if some of what's up there is invisible
And terrifying.
That's your takeaway message.
It's honest. All right, I'm Marcus Chen.
And I'm Dr. Elena Vasquez.
Thanks for listening.